Good morning, everyone. Thanks for coming. I'm Abel Bernabeu from Esperanto Technologies. I also chair the graphics machine learning special interest group within RISC-V. And in this talk, we are going to review what's missing on RISC-V for the task of building a shading core for graphics. And it's basically intended for a graphics architect that is considering to build an OpenGL ES 2.0 solution with RISC-V. And I make a couple of assumptions. First is that you may want to use SPIR-V as intermediate representation for your shaders, and also that you may want to achieve an extraction count that is not much worse than what you get on other commercially available solutions based on proprietary ISAs like AMD's RDNA2 or NVIDIA's PTX. So yeah, we want to be within a range of not more than twice as many extractions, which is a good metric to try to achieve. And well, first of all, let's make a couple of introductions. On the left-hand side, we have SPIR-V, which is a standard portable intermediate representation, and the V stands for Vulkan. It's actually a superset of all the features released on any programmable shading standard since 2004, which is a lot of functionality, actually more than we need for this task. And it's got extensions for GLSL and OpenGL. And on the right-hand side, we have RISC-V V that I don't think it needs many presentations in this venue. And we are going to try to match the functionality from the left-hand side into stuff from the right-hand side. Well, first of all, SPIR-V supports the same data types that we have on RISC-V and a few more. So in addition to vectors, we have matrices, and we also have scalar data types that are specific for graphics, like images, image views, and samplers. There are a few more, but they are not strictly required for graphics, so we are going to just omit them in this talk. And well, the first thing that we saw in the working group is that there is a bunch of math functions, quite general purpose, that are required for GLSL, but are not yet available in the RISC-V V specs. There are three groups of instructions that fall into this category. There are rounding instructions like floor and seal, and we also have this OPIS normal instruction that in order to be supported would likely require an extra bit on the mask returned by VF class. And we also have a bunch of transcendentals, which would take plenty of area to implement if we try to implement all of them in the hardware. But the good news is that we reviewed what AMD and NVIDIA are doing in the published ISAs, and they only support 4 of those. And that's something that is possibly achievable within RISC-V. So we have sine, cosine, and base 2 exponential and logarithm. Well, there is also something that is radically different between SPIR-V and RISC-V V, and is that the way that work is distributed across execution units. So in SPIR-V, there is this concept of work items. So a work item is basically a compute task that produces one vector or a matrix at a time. And in RISC-V V, the concept is a bit simpler. Basically, you have vectors and you produce one vector element at a time. The big difference between supporting work items or not comes when you do reduce operations. Imagine you want to do the max of a 4 elements vector within a work item. So basically, you would want to produce one output per each of the work items for SPIR-V. But on RISC-V V, what you would get would be just one maximum value for the whole vector. There was actually this divided element extension that was Appendix A of the RISC-V V spec, but was dropped in the last second. And that was a big loss for graphics, but it's also an opportunity for building back better. So it doesn't sadden me that it's not yet part of the standard. One other thing in which we think that there is work to do is matrix products. So in SPIR-V, we have 3 instructions that are special cases of matrix products. And the 3 of them could be addressed with new functionality. At the moment, we could fall back to the v.vv instruction that does dot products, but that implies that we decompose the work and we take freedom from the microarchitecture to implement those things with more resources. Another area is the texture sampling, where we have SPIR-V instructions that would require new CSRs, likely. They are at the top, and they are needed for defining texturing state. And we need at least one new instruction for doing sampling. And there are 3 more that are just particular cases of that one, and they can just fall back to a very general sampling instruction. And last but not least, there are data layout transformation instructions that they can be supported easily with vrgather.vv, but one may need like an optimized way of loading immediate values on the indices registers. And doing that by hand is going to be a bit cumbersome. And ideally, one would like to have like an instruction for doing that in one step. So the good news is that this allows you to do things like swizzles, matrix transpose, and it doesn't add any extra logic on the register file. And like this is a way to go, having these new immediate load instructions. And similarly, there is this partial derivatives case in which basically you are subtracting values across neighboring elements, either horizontally or vertically. And this case would also benefit from like an optimized way of loading immediates for index registers. And well, finally, I would like to thank everyone from the graphics and machine learning special interest group who have been actively contributing. And well, I want to say also that an important takeaway message from this talk is that if you face the problems that we've been highlighting here, first, you are not alone. Second, there is a way forward, which is joining our group and help to drive the solutions. And yeah, we want this talk to be like a way of telling you what are the problems and what's the kind of work that you would do if you contribute to our work group. So that's all. Thank you. Do you have any questions? Okay, yeah, you can also reach me later, or I'm going to be available here for the rest of the day. Yeah, thank you, everyone. Oh, yeah, please.
So why do you need a full ISA extension for this? Can you not use the custom instruction space?
Sorry, but why do we need that? Which kind of extension?
Why do you need a full ISA extension? So you're proposing to change the RISC-V vector extensions, I think.
Well, it's just adding. So what is in there is good. And it's just, well, our work would be more like giving you an optional spec that you can implement or not, and it gives you extra instructions. But whatever is in there, it is good, and we've been reviewing it, and it looks good. It's just adding, not changing.
Okay, thank you.
So, yeah, well, yeah, maybe I could also, because I have one, do I have one more minute? So, yeah, but I was expecting also questions about why are you picking OpenGL ES 2.0 as a baseline set of capabilities rather than something more modern. Well, there is actually a good reason for this. Well, first, when you want to approach a complex problem, you better set yourself for success by setting the bar low enough, and later you can start adding more functionality. And the other reason why the bar is here and not much lower than that is that OpenGL ES 2.0 is the first programmable shading standard, which is the foundation for all the subsequent delta increments that the other specs are adding. If we had chosen anything much lower than that, it would mean that we would have to scrape it all for starting from scratch when going from non-programmable to programmable. Yeah, the bar has to be low, but it cannot be below ES 2.0. That's the takeaway message. Okay, so thank you, everyone.